How about if you have if you have a set of data that involves derivatives, not just data points, not x1, y1, x2, y2, but something involving also the derivatives. This is pretty common in different engineering applications, where you have first order, second order, or whatever order derivative as an input. Let's illustrate this by using first order derivatives, and you can extend that. And just note before going through this that you still have to have n plus 1 points to be able to interpolate an nth order polynomial. So if, for example, if you have 4 data points, remember, you can interpolate a cubic polynomial. If you have 3 points only and 1 derivative at one of these points or any other point, then you can still interpolate an nth order polynomial because they are just 4 pieces of data. Okay, finally, let's use the generalized approach, but in a little bit modified way. Let's assume that we have, say, m points. At each point of those m points, you have the derivative and, you have a value of the function and the slope of the function. So again, you have 2m data points. Half of them are just x and y, and the other half is x and dy by dx, or what we call y prime. So we can interpolate 2m plus 1 plus 1. Anyway, just let's assume that we can get an nth order polynomial, so you have n plus 1 data points. Now, again, just using the same interpolation, here you are, y of x equals summation ai x to the power I, which can be written as h of x times a. It's the same procedure where h is the x vector and a is the coefficients vector. But now, instead of all x's and y's, we will have y1 corresponding to x1, where you can now create this h1 just like the previous step, but at x1 you also have dy by dx, or y1 prime. Here what you need to do is differentiate the function you had. See here, if you differentiate dy by dx, you actually are differentiating h with respect to x, because a's are all constants, so you get dh by dx. So when you substitute with the slope point at x equals x1, all you need to do is get the derivative of h with respect to x, which again, if it's 1x, x squared, x cubed, you end up with 0, 1, 2x, 3x squared, and so on, and substitute with the value of x1 to get what we will call here h1 prime. So the second equation you got was y1 prime equals, which is the data point, equals h1 prime at x1 multiplied by the unknown coefficients a. When you set up all these, when you plug in all these data points, you obtain again an n plus 1 equations, but this time they are arranged a little bit differently. It's y1, y1 prime, y2, y2 prime, and so on until you get ym and ym prime. Remember, in our example here, what we're doing is interpolating a special set of data, where all what you have is the data value, the value at the point x, and the derivative at the same point. You may have any other combination, but if this is what you have, you can still use these steps. Again, finally, you obtain a transformation matrix. This time it will not be the same like the previous transformation matrix, but again, It's an n plus 1 times n plus 1 square matrix that you can invert to obtain the coefficients A. So here you are, just invert them to get the function, or use them to get n of x the same way we did before to obtain the Lagrange polynomial. This is a very straightforward thing. As I told you, you can just modify it a little bit to obtain a similar, to obtain the steps for any combination of data sets. You don't have to have half the data as x, y, and the other half as x and y prime. You can have whatever combination, and then you start fitting the polynomial that's suitable for you.